The topic for today is magnetic energy field in the universe. And we have Sam here with NASA.
Yeah, hi.
Hi,
Hi.
how are you? Thanks
Yeah,
for
doing well,
the time.
thanks.
Can you tell us a little about yourself?
Sure. My name is Dr. Sam Richards. I work for the University Space Research Association as an instrument scientist for NASA DLR's SOFIA mission. This is a Boeing 747 SP that we have a big telescope that we put inside. We took out all the seats, put the telescope inside, a little mission control inside as well. We fly that up into the stratosphere, somewhere between 40 and 45,000 feet. And then we open this big garage door on the side of the aircraft, and we look out and we look at stars, galaxies, dust, gas, black holes, all these kind of different things to try and understand the universe through astronomy and astrophysics.
So what kind of instrument do you use to look at the universe?
Yeah, so we have 5 different instruments at the moment on SOFIA. So SOFIA is a telescope. It's just like the lens of a camera. And then we have 5 different instruments that we put on, and those 5 different instruments do 5 different things. In astrophysics, a particular instrument is designed to target a particular type of science and measure a particular feature in the energy spectrums. So when we've got these 5, we have images, so just cameras that just take pictures, things like that. We have spectrographs, so they look at the chemical signatures. We have low resolution spectrographs, we have high resolution spectrographs, so different wavelengths. And then we have a particular instrument called Hawk Plus, which has a polarizing filter on it. So it kind of takes images, but kind of with a polarizing filter.
Okay.
Kind of like your sunglasses have polarizing
Yeah.
lenses and things like that. And if you tilt your head, you're going to get bright and dark and things like this. So if we kind of tilt the filter on Hawk Plus, then we can detect how bright the light coming from the dust is in different polarizing angles. And then we can reconstruct that and understand how strong a magnetic field is in that particular region. This is really interesting because the dust is kind of like a little grain of rice or something like this. It's much smaller than rice, something like this. It's got magnetic components to it, and it's ferrous in that way. And so when you have a large magnetic field, kind of like little iron filings, when you put a drop of magnet into iron filings, the iron filings all kind of line up with the magnetic field. You can do a high school experiment with dropping magnets and filings.
Do you guys give these universes names when you discover them?
Well, yeah, so we're looking, these regions that we're looking at are different star forming regions. So within our galaxy, we have different star forming regions, and we're trying to understand how magnetic fields regulate and have feedback processes and things like that in these star forming regions, how new stars are being formed, why some star forming regions form big stars, why some form smaller stars, and why the chemicals interact in different ways. And then we look at some fields which are external to our galaxy, so looking at other galaxies. And then when you're looking at kind of distant galaxies like that, typically you can't get a lot of spatial information. But some galaxies are kind of close to us in the scheme of the universe. And then we can understand the kind of larger scale, galactic kind of scale magnetic fields, and then the drivers in the environment between galaxies and things like this.
And what are some of your insights after observing these little universes and the energy fields?
Yeah, so some interesting things come up. There's a particular galaxy that is not too far from us that is very energetic with its star formation. So it's in the center of the galaxy. It's belting out all of this material because of star formation and things like that.
It's kind of like a firework.
Yeah, it's pretty interesting, this particular galaxy. And And what's happening there is that typically the magnetic field controls the environment, but
Uh-huh.
because the star formation is so extreme, it's pushing and it's like warping the magnetic field. So this is a particular instance where a physical process, so like star formation or something like this, is overriding the strength of a magnetic field. And it's pretty interesting to see this. Typically, the magnetic fields are controlling the flow of different gas and dust and things like this. But in some situations, there's a process that overrides it because the strength is just too high. So we look at all these different environments. We look at all these different scales of environments. So going from large things, galaxies, all the way down to kind of small things near stars and stuff like that,
Yeah.
to try and understand the big picture of how these magnetic fields are flowing in and how they affect their environment.
Yeah. Awesome. And what are some of the? I mean, you must have some favorite universes that you like. So what are like the top three universes, like or stars, or even magnetic fields affecting it that you like the most?
Yeah, so this particular one that I mentioned, this galaxy is M82, I believe. I believe that's the name. It's Messier M82. This particular one I really like because it's really cool because it's got this extreme star formation coming from
Yeah.
this galaxy. Um, and then there's a dwarf galaxy that's actually very close to the Milky Way. We call it the Large Magellanic Cloud,
Mhm.
and it's you can see it with the naked eye from the southern hemisphere. So if you go to Australia or South America somewhere, you can kind of see it. And it kind of looks like a big fuzzy cloud blob in the sky. There's two of them. There's the large magnetic cloud and then the small magnetic cloud. But the
Okay.
large magnetic cloud is of particular interest because near the edge of it, there's a very extreme star formation region called 30 Doradas. And this particular region has been studied of great interest with Hawk Plus, this instrument on SOFIA. And this data set's actually public, so anybody can go to Sophia's website and go and explore this data set.
Oh, awesome.
And it's really interesting because we've observed it in different wavelengths
Mhm.
or using Hawk. So because light is um, blocked by different sizes of particles and things like that, kind of dust, imagine light getting hit by dust and stuff like this as well. If you look at different wavelengths, you can see further and further into a kind of like a dusty region. So the shorter wavelength lights get blocked quicker, so you can only kind of really see the surface stuff.
Yeah.
And then when you look at different longer wavelengths, you can kind of probe further and further into the core material. So we've got I think 4 different wavelengths that we've looked at with Hawk Plus, and so we kind of got this kind of 3D picture of what's going on with the magnetic field,
Mhm.
and then also what's going on with where the dust is located and where the star formation and what's going on, and what's going on with the driving mechanisms there. So these 2 particular regions are really cool. And then the other ones we're looking at are external galaxies, is AGNs. These are
Okay.
have very active kind of supermassive black holes that are spewing out these big jets of material, high energy material. And around these AGNs, you typically find these a torus, a kind of donut of dust that kind of surrounds the AGN. And what Hawk can do as well is kind of understand the environment of these torus disks, and it's really interesting. And the instrument scientist Enrique Lopez Rodriguez, who's the instrument scientist for Hawk, he is studying these particular regions in great detail. So it's fantastic to see, and you can read about this in literature and also on Sophia's website in press releases.
Awesome. Yeah, the second one reminded me of Burning Man for some reason. Just really walking on the playa with
Yeah,
like different levels of sand, and then all the dust storms. Um,
yeah. So so you can see
you can see, yeah, different layers
through
to
the
it
dust.
as
Yeah,
you walk. That's really cool.
it's basically like how if in the optical, if you've got a let's use Burning Man or use a burning house or something like this, right?
Yeah.
You can't, like with a mobile phone camera, you can't see through the dust, the smoke and stuff like this from a
Yeah.
building. But if you go to like the heat sensing kind of goggles and things like that, you can see further into the building. You can see where the flames are and stuff like that. That's
Yeah.
because the heat sensing kind of goggles are in the infrared, and so you go into a longer wavelength. You can get through the dust and the smoke. Like that's basically what's going on there. So it's you go to a different longer wavelength even still, like
Yeah.
because the infrared that are in these kind of heat sensing goggles and things is very short wave infrared. We're looking with SOFIA the kind of longer wave. So this is like pure emission from dust and different chemicals.
So, is there any like materials that you see as well in the universe, or or is it just magnetic fields? And we just wanted to like,
Yeah. So as I said, like with SOFIA, there's different instruments look at different things. So for Hawk, we're particularly interested in these magnetic fields. So we're looking at dust, just the emission from dust. It sounds boring, but it's actually really interesting. Like dust is up in the
really
morning.
steady dust.
It's strange to say that, but it's actually very interesting astrophysics.
Don't they have different colors?
Yeah, so the different colors are just based on the different wavelengths and things like this, and they're made from different materials, and that's very interesting as well, because they regulate heat differently from different compositions of dust and things. But particularly, we use other instruments to look at like the gas signatures, and this is really interesting because when we use spectroscopy to look at gas signatures or molecular lines, these are like these emission lines and things like that, and we can probe some really interesting chemistry, so very kind of cosmic chemistry of what's going on in these regions and why even things like solar systems are formed in the way they are, because of the type of chemicals that surround the system as it's being born. And so why planets have certain chemical compositions and things like that, you can kind of understand that based off from the cloud that it all gets formed from. A particular result was really interesting was earlier this year we released a detection of helium hydride. This is one of the first, basically the first molecule, if you will, that gets formed after the Big Bang. So it's really interesting. So as the Big Bang happened, and then in the big expansion, things are still very hot, and as things cool down, you then eventually reach a temperature where you can start forming molecules. So the energy is below the bonding energy. So if the energy in the environment is above the bonding energy, then those bonds will just break and you can't form the molecule. But once things cool down enough and you can start sticking together molecules, one of the first ones, basically the first one to form, is this helium hydride molecule. And we've never been able to detect it in space, in the environment of space before. We've been able to find, we know its existence, we know it in the labs, and we've been able to do things like that. But to see it in a natural environment, we've not been able to detect it before. But earlier this year, one of SOFIA's instruments called GREAT was able to detect it in a planetary nebula. And this is what kind of like after a star has exploded, then you can form these kind of planetary nebula, and that's where these energies get very high and then they start cooling down. And so this is like a good region where you can get at the same temperature range that you would have formed in this kind of early universe. We were able to detect helium hydride. So it's a fantastic result for the team there, and there was a big press release on that, so you can find that on SOFIA's website as well.
Super cool. So I was telling my friends about about this chat, and some of them have a few questions, so I'm gonna go through them, and if you don't apply, let me know.
Yeah, sure.
Okay, so my friend Robert asks, is there a potential effect on weather and migration pattern, military or civilian use?
Of SOFIA?
No, military or for basically the magnetic energy field.
Oh no, so Sophia's doing astrophysics. So we're looking up out into the universe, not kind of anything locally. And actually, we want to get rid of the local signals. We get rid of the sky background and all this kind of stuff. It's all noise to us. So we look at the astrophysics. So we look up into the stars, the galaxies, things like that. We don't do anything locally. The most local object we've ever detected is the moon. we look and study the moon sometimes.
We haven't seen any.
We don't do anything locally. We don't have any instruments to detect anything locally.
But you don't see like interstellar, like alien ships?
Oh no. No.
And then my friend Angela has a question about your view on morphic resonance, where memory is inherent in nature and natural systems inherit a collective memory. So I guess what it means is, do you see life with these magnetic energy field in terms of patterns and memories, behaviors?
That's, I guess, more of a question for a philosopher rather than a but yeah, I mean, I say the magnetic field science that we're studying it is really the core physics of what's going on with these magnetic fields, and how they regulate the physical processes of atoms, molecules, the formation of stars, galaxies, systems, things like that. That's the science of what's going on there, and I know I'll leave that interpretation up to
Okay.
philosophers, I guess.
And then one of my last question from one of my friends, Susan. Is there any chance of using these magnetic fields to lower our utility bills?
That's an interesting question. Okay, that's a really interesting question. I would have to really think about it more, and I'm sure there's been a lot of studies. I mean, we do use magnets in electromagnets. I mean, that's just like when we're using dynamos and things like that, we're using electromagnetics to generate electricity and all this kind of stuff. So from hydro dams and all this kind of stuff, they're using electromagnets for a lot of that stuff.
Okay, so maybe potentially then.
Well, yeah, we're talking, the magnetic fields we're talking about are extremely weak on the scale of using for energy, and however, because the scale of these magnetic fields are so large, they affect even the smallest kind of dust grain and things like that. And so it's the type of system that we're using that we're detecting are we can't generate any electricity from the astrophysics that we're looking at. I don't see it directly, but however, understanding magnetic fields is definitely of interest for humanity, and using magnets locally on Earth. However, the scales are very different. That's more of a material science, physics kind of question, and energy generation professor type thing, rather than looking. I don't think we can wrap a copper wire around a galaxy.
And when you go up there, is it in a spacecraft?
So we're in an airplane. So we're in a 747 airplane. So like any other kind of commercial airplane, it's a 747. However, we do have this P on the end of our name, so it's 747 SP. So the SP is special performance, and what this is a particular type of 747s that Boeing made, which are a bit shorter than a typical 747, and they're able to climb higher and faster and things like that. So for SOFIA, we look at the infrared, and the big, like I say, contaminant, or the reason why we can't do this from the ground is because in the atmosphere we have water. And water is a very good absorber of heat, and infrared light is basically heat. And when the infrared signal comes down, it gets absorbed by the water in the atmosphere. So we need to get above the water in the atmosphere. Okay. Now, we can either go to space, but that's very costly, and you have to lock in your technology. There's not much room for flexibility. But we do have, we have had many infrared telescopes in space. It's Spitzer, Herschel, all these kind of instruments. So, but with SOFIA, what it enables us to do, because the water in the atmosphere is mostly contained to what we call the troposphere. The troposphere is basically everything kind of from ground level up to the tropopause. The tropopause is the layer that separates this kind of ground layer to the stratosphere. The tropopause is typically around, I don't know, 40,000 feet in America. It depends on where you are on the planet, what season, all this kind of things, what the atmosphere is doing, pressure systems, all this kind of stuff. But it's typically maybe like 35,000, 40,000 feet, or something like that. So if we can get above the tropopause, then we're basically above like 99.9% of the water. And then we can observe the infrared light from the airplane. You could also put instruments and telescopes on weather balloons, these big kind of like
Oh yeah,
balloons
yeah.
you launch them from Antarctica and stuff like this. So we do that sometimes as well. There's some restrictions in terms of the flexibility of your science when you do that type of mission. So with SOFIA, it enables you to get the most flexibility of the science, the most opportunity to upgrade your instrumentation, keep current with the current astronomy questions, and also come home every day. So that's nice. So I get to go to my own.
How often do you travel to space?
So we typically have 4 flights a week, 4 to 5 flights a week or so, and and then for a particular instrument, it might be on the telescope for a few weeks at a time, maybe 3 weeks or 4 weeks or something like that at a time, and then we switch instruments, and then we go to a different instrument. And different instruments, as I said, are tailored to look at particular science questions, and some look at the chemical signatures of gas and these emission lines. Some look at dust and take pictures and stuff like this. So every year we open a call for proposals from astronomers, and so anyone anyone can submit a proposal to SOFIA, and then we have a committee that's independent from SOFIA, that a scientific committee that ranks them, and then we pick the best ones, and then they get sent to us, and then we go and get the science for the astronomy community, and then that's that kind of year by year.
How big is the team?
The SOFIA team is quite large because we have, scientists, we have engineers, we have, if you then include also the aircraft, we have aircraft mechanics, avionics people, pilots, and all that kind of stuff. So it's a couple of hundred or something like that.
Wait! You guys took a whole airplane, like with 200 people?
Oh no! So when we're actually on the airplane, so in terms of the wider team that's in offices and all this kind of stuff, like a few hundred or something. But when we're talking about like on the aircraft, I think the minimum is like 12 or something like that, because you have to have certain safety people, and then you have to have somebody looking after the telescope, somebody look after the instrument, and then a mission director and all this kind of stuff. So it's about 12 people, but typically we're somewhere between 15 and 20, because we actually invite some guests on board, and those can be press, they could be VIPs, or actually we have an educators program. So we actually invite school teachers, high school teachers from around the country, but and that's run through the SETI program.
Oh yeah.
And so we have a partnership with them. They're through their Bay Area, the Mountain View offices and things like that, and they organize for us the teachers. So they go and run that program, and then they say these teachers come on board, and then we have lesson plans for the teachers, and then they go back to their classrooms and talk about their experience and teach more about astronomy and SOFIA and science to the children. So unfortunately, we can't bring all the children on board. there's a lot of FAA regulations with an engineer and aircraft and things like that. But we do open days as well. So actually, there's an open day coming up. So on the 18th and 19th of October, at the Ames campus, on the 19th of October, there's an open day where the public can come and look at SOFIA. So this will be. We're not going to fly, but we're going to be on the ground, and then people can come and do a little tour of SOFIA, and then talk to us, the team, learn more about SOFIA and the science that we do, and that'll be at the Moffett Field base in Mountain View area in the Bay Area, California.
How many SOFIA is there? It's just
Just the one.
Just one?
Yeah, it's just the one airplane. Yeah, and one telescope. Yeah.
Okay, cool. I just want to make sure.
Very custom airplane, in that regards. It took a long time to modify it to be able to house this telescope, and then we're now into kind of full operations and full science. We've been doing that for about 6-7 years now, kind of full science mode.
So what do you think is the future of SOFIA and the future of magnetic energy fields?
Yeah, so as I say, like we're magnetic energy fields in the universe and things like that. It's kind of been a little bit of a neglected area from astrophysicists. Not all astrophysicists, but in terms of the wider scene, because it's actually very complex. It's a very difficult thing to try and understand. And previously, our theoretical models to try and understand about star formation and stuff like that had other areas that they needed answering first. And so there's other physical parameters that needed better understanding. We've kind of got those down, not entirely, but we've basically got those down. And now the models are really having to think about magnetic fields. So Hawk Plus has come along at a time where the astronomy community is actually very excited about learning more about magnetic fields and how they affect the theoretical models that are being used to predict things like star formation models. And so we see a lot of interest from the astronomy community when we do these kind of cycles of call for proposals. So people submit applications to use SOFIA. We see a lot of interest, even still. Like we just had a round actually, so it closed earlier this month. The deadline closed earlier this month, and we got hundreds of applications came in, and then we can over the coming couple of months we will send those off to the scientific committee for evaluation, and then we'll go through and then we'll pick out the ones that best fit within the parameter space of SOFIA. And will provide the best data and science for the community. And so, yeah, there's a lot of interest in for using SOFIA. So it will keep producing as long as it can keep producing. So
my last question is, for the community, and for people who are interested in science and space, what is that one advice that you want to provide to someone who, is inspired by the universe, space, physics, and what you do? And say they're like now in high school or college. What are really some suggestions that you have or recommendations, whether it's professionally or if they're interested besides looking at the website?
Yeah, sure. Yeah. No, so I'll take that in a couple of parts. The first part is just the more general kind of like science stuff. So, as I call myself a scientist or an astrophysicist, right? I'm just curious about stuff. I'm curious about a lot of stuff, but space is cool. So
space is awesome.
My curiosity there. But it really is just keep your curiosity up. In a general sense, be curious and think about things pragmatically in terms of the flow of the flow of physics. You might need to understand something, in its core mathematical principles and stuff like that. But try and understand like the flow of things, how the logical flow of science, and become curious about different areas. And it's fun. It's just fun, to learn about these things. And there's tons of resources for people that just want to learn more. But you don't have to go into the full math stuff if you don't particularly mind. But it's interesting. I find the math beautiful because it is the language of describing what's going on. So it's really cool. In terms of a more kind of professional take on things, for university students or so, and if you're in, or even if you're in high school, or if you're thinking about going into this type of career and things, it really is just apply yourself and seek things external to just the core education. What I mean by that is, don't just turn up to lessons and you might be very good at exams and and course material and stuff like that and do very, but what we're really looking for is people who just go and try things. So research projects or internships, all that type of stuff really goes a long way when we're trying to select people to join this type of science. And so if you're in university and you're studying physics or astrophysics or anything like that, then finding a professor or a project for over the summertime, or even just during the course semester, as just something that you do on the side, is definitely what you want to do to build your experience and build your expertise for going forward. As an example, like that's what I did, and that's why I've ended up here. So actually, in high school, I got a D in physics, so that's fun.
No way.
Yeah, I mean that is true. It's just I high school didn't fit me in terms of my education and things like that.
Yeah, yeah. I
And
took
then I
physics in
went,
high school, and all I remember was just the math,
yeah,
calculus.
yeah. But I thoroughly enjoyed it. But for some reason, I don't know, I got a D. I don't remember high school life too much. But but then I went to university and I found that this type of education system is much suited to me.
Yeah.
People they talk about people bloom later in life or whatever. But it's just like that style of education fit me. And I found a school where it wasn't the best school. It wasn't Oxford. I'm from England, so it wasn't Oxford or Cambridge. It was the University of Hertfordshire. So it was a kind of like not even one of the red bricks, which is like the Ivy League kind of England. And so people were asking, well, why are you going there? All this kind of stuff. One, because of my grades, I couldn't get into Cambridge and Oxford, but also this astronomy department was actually equally ranked in terms of the professor's scientific output. So if you look at like Oxford and Cambridge and stuff like that, and you look at this school, like they're actually on par, and they have a lot of collaborators that work. But it's a much smaller school, and the classes are much smaller, and there's more opportunity to do projects. And so I was like, oh, that sounds fun. I get to go and be hands-on with these kind of small telescopes, kind of that they had in the education facility. Do summer projects. Work on some research papers in the background with some professors whilst the course is ongoing. And then I did a research year in the University of Sydney, where I worked on a project there through one of the contacts from my professors in England, a professor in the University of Sydney. They took me out there for a year to do a research year in the University of Sydney.
That's awesome.
I worked on a new instrument there ended up being called SAMI, and this was a new way of looking at galaxies and their spectrum.
Yeah.
And then that instrument became quite successful. So that prototype instrument became quite successful. Went back, finished my undergraduate in England, and then came back to the University of Sydney for my PhD, which was finishing off the second phase. That much better. It's not a prototype. It was actually a proper instrument, but the same kind of science. And then did an astronomy PhD on the science of that instrument, as well as some other novel photonic technologies. And then after that, I got a job at here working with SOFIA. So it's it's kind of like but it was all because at university I was more interested in like doing these research projects and working with professors outside of class, doing well in class as well, and being studious there, but just being interested in fun and going to chase these other projects and learning more and more. And if you do that type of thing in university, then when you're looking for PhDs, or you're looking for scholarships, or you're looking for early career jobs, like that's the kind of stuff people will look for.
You have direct experience.
Yeah, it's when people talk about like you need a degree in this plus 5 years experience, for an entry level job. It's like, well, how do I get 5 years experience? This type of thing they're actually talking about, right? Yeah. They're not actually talking about 5 years of full-time work experience. They're talking about 5 years of experience in the field.
Yeah.
And so that even from day one in university, you've gone, maybe the first summer you've done an internship, or you've done some project or something like that. And in astronomy, different universities are very accommodating to cross, to go to a sister school or something like that for a summer. Different projects, and NASA themselves run an internship program, and SETI as well, and like all these different research bodies in the US run different research grants and things. So. SOFIA ourselves, like, because we're under NASA, we're a NASA mission, we get internships. I think we have a few at the moment, and then we also, because the SOFIA mission is actually 80% NASA, 20% DLR, which is like the German space agency.
Okay.
And then they they also send internships and stuff like that. So we have a strong partnership with Germany. We have a lot of Germans on the mission still that look after the telescope. That's kind of their responsibility there. So we get to interact a lot of international people in that way as well.
That's like super super awesome.
Hmm.
My closest, I think I was, in terms of looking at the Milky Way, I was at Yosemite, and I went off path.
Yeah.
Just to look at that at like 3 a.m., 2 a.m. in the morning. I think that was like the closest to me in terms of getting to space.
I mean, it's one of these unfortunate things, electricity and lights are like really important for life now, and things like this. It's why we have a lot of these things.
Yeah.
However, it unfortunately, disables our ability to see the sky, where, a couple of 100 years ago, you would just be living and then you would just look up and see the Milky Way. Whereas, these days you have to go out, but it's easy to get out in a car and drive a few hours away, and from these major cities, and you can see the sky. It's quite easy to be able to go out. I mean, like even from like I don't know, major cities like LA or something like that. All you need to do is drive a couple of hours out of LA and just pull over on the side of the road, wait 30 minutes with your eyes shut, and then look up. I mean, like it's as easy as that. I mean, however, I do recommend the southern sky. I am a bit of a bias to the southern hemisphere because you can see the center of our galaxy, the Milky Way, and you also get to see the small and the large magnetic cloud, and it's quite dramatically different. My time in Australia was quite precious because you could just go out to the Blue Mountains, which are pretty close to Sydney, and then just look up and see this magnificent sky. So,
you see the Northern Lights too, or?
On Sophia, sometimes we do, yeah. So we fly sometimes north and we enter into Canada a little bit so we take off from Palmdale, which is just outside of LA in the Antelope Valley, and when we're based in the US, and then we fly kind of these starfish type flight patterns, but sometimes we go quite far north, and then we enter into Canada and we can see some northern lights. But the most spectacular ones is every year we actually go down to Christchurch in New Zealand. So during the summer months in the US, the weather systems are just too crazy, so they push all this water vapor too high in the atmosphere. So there's not really any good science, great science that we can do from there. It's better to go to New Zealand when it's winter down there at the same time, and so all that water is really low, and so that it doesn't take as long to get above the tropopause, and so we can get some fantastic science out there. So we go down to Christchurch every year during the summer months whilst the weather's a bit crazy in America, and then we fly from there, and sometimes we go south as well from New Zealand, and New Zealand's quite far south itself, and then we get to see the southern lights in dramatic fashion. And so if you go to the Sophia's Facebook page or Instagram or even the website itself, you can see photos of recently from this year's deployment. So we a couple of months ago only just came back from New Zealand, and we had a gentleman called Ian Griffin, who's the museum director at I can't remember that, Otago or Otago, I can't remember the name. It's south in New Zealand, south of Christchurch along the coast. Anyway, he's kind of like he is an astronomer background and things like that, but now he does kind of like more of the kind of outreachy type things. And he brought on some fantastic camera gear and took these amazing photos of the southern lights, and like the cockpit it looks like you're flying through them. I mean, it's just crazy. I mean, you're not. I mean, it's too high, but but it looks like that you are. Yeah. You're flying directly under them.
I was in Iceland last year, just catching the northern lights. It's super beautiful, and I've seen the meteor shower before in like Bora Bora. So I mean, those skies are just incredible. And how do we find you?
So I'm personally I'm on Instagram as at that NASA guy. So it's a pretty easy tag for me. And then you can find me through that in my bio or whatever. You can find links for everywhere. On Instagram as well, that Sophia is Sophia Telescope, I think it is the handle for Sophia on Instagram. But if you go to Facebook as well, then you can search for Sophia. You have to put the long name in because Sophia is a pretty popular name. It's SOFIA, Sophia, and it stands for the Stratospheric Observatory for Infrared Astronomy. So that's the acronym. And you kind of have to type all of that in Facebook for it to get the page. It's a bit annoying, but you have to kind of do that. But the website is www.sophia.usra.edu, I think. And then you can find all the links through that one. There's I think at the bottom there's the social network links. And we have, YouTube. We post videos there, and Twitter, and all these kind of other things. So.
Yeah, I think I follow you guys on YouTube, especially the space and launch things.
Yeah.
Just want to thank you for your time.
Yeah.
I was really excited. I met Dr. Samuel at Silicon Valley Comic Con.
Yeah, it was. Yeah.
That was I was just walking around NASA. I was really geek out on it. I that's why I went there. I love NASA and space. So thank you for your time. I really, really appreciate it.
Yeah, pleasure.
Bye.
Yeah, thanks a lot, guys. All the best.